Myself, Dr. P. Soumya, working as an assistant professor in the Department of Chemistry, Institute of Aeronautical Engineering College. In this session, I am going to discuss about Nernst equation and its applications. In this session, I am going to cover Nernst equation, application of Nernst equation. Nernst equation and applications of Nernst equation. So, Nernst equation. Nernst equation was introduced by the German scientist Walther Hermann Nernst. German chemist Walther Hermann Nernst. So that's why this equation is called as Nernst equation. This equation is called as Nernst equation. The Nernst equation provides the relation between the cell potential of electrochemical cell, the standard potential, temperature and reaction quotient. The Nernst equation provides the relation between the cell potential, that is E cell, and the standard cell potential, that is E naught cell, and temperature and reaction quotient. So even under non-standard conditions, the cell potential of electrochemical cells can be determined with the help of Nernst equation. So we can, with the help of Nernst equation, we can determine the cell potential of electrochemical cell at standard conditions as well as non-standard conditions. The Nernst equation often used to calculate the cell potential of electrochemical cell at given temperature, pressure and reactant concentration. The Nernst equation is often used to calculate the cell potential of electrochemical cell at any given temperature, pressure and reactant concentration. So this is the derivation of Nernst equation. For deriving Nernst equation, first we have to consider a metal which is dipped in its own salt solution. So if we take zinc rod, it should be dipped in the zinc sulfate or zinc chloride. If we take other metal, that is if it is copper, so it should be dipped in copper sulfate solution or copper chloride, etc. So like this, first we have to consider a metal which is contact with its own salt aqueous solution. So the reaction of metal losing electron to become an ion and the ion gaining electrons to return the atomic state are equal feasible and are equilibrium state. Means the reaction of metal losing electron means the reaction, that losing electron reaction means oxidation reaction and metal is losing reactants, losing electrons and forming metal ion. So this is oxidation reaction and metal ion gaining electrons and forming metal. So this is reduction reaction. So these both reactions are in equilibrium state and both reactions are feasible. Both oxidation and reduction reactions are feasible and both are in equilibrium state. Means metal is converted into metal ion and metal ion is converted into metal. So oxidation and reduction. So these both are in equilibrium state and both reactions are feasible. So here we are taking reduction reaction. For the derivation of Nernst equation, we are taking reduction reactions of metal ion and which is taking n number of electrons, n moles of electrons to form metal. So this is the reduction reaction. In this reduction reaction, n moles of electrons is taken up by ion against the reduction potential E reduction. So here n moles of electrons are taken by the metal and to form metal ion to form metal. So this potential, the potential which is developed due to this reduction reaction is denoted as E red. So here E reduction, E cell of reduction. The potential of cell during the reduction, it is denoted by E red. The work done in the movement of electron. So here movement of electrons are taking place between oxidation and reduction reactions. Here we are taking reduction reaction. In this, electron movement is taking place. So the work done in the movement of electrons is indicated by W reduction. Here this is reduction process. That's why work done is also denoted by work done in the reduction process equal to NFE reduction. So this is taken as 1. This is taken as 1. So where F is a Faraday. F is Faraday. So the value of Faraday is 96,487 coulombs. And also we can write as 96,500 coulombs. So what is Faraday? Electrical charge carried by 1 mole of electrons. What is Faraday? The electric charge carried by 1 mole of electrons is called as Faraday. The value of Faraday is 96,500 coulombs. So we know that the change in free energy, the change in Gibbs free energy is an indication of spontaneity, and it is also equal to the maximum useful work done in the process. Maximum useful work done in the process. Change in Gibbs free energy. Change in Gibbs free energy is denoted by delta G. This is an indication of spontaneity, and this is equal to the maximum work done. Maximum work done in the process. So we know that delta G is negative. If delta G is negative, that reaction is feasible reaction or spontaneous reaction. Spontaneous reaction. If delta G equal to positive, so non-spontaneous reaction. Non-spontaneous reaction. So the change in Gibbs free energy is an indication of spontaneity, and it is equal to the maximum useful work done in the process. So by combining this Gibbs free energy and work done, we will get, so W reduction equal to NFE reduction equal to minus delta G. So from this equation, delta G equal to minus NFE reduction. This is equation 2. This is equation 2. The change in the free energy at standard conditions. So what are standard condition? Temperature should be 298 Kelvin. Pressure and concentration are 1 atmospheric pressure and 1 molar concentration. These are the standard conditions. So the change in free energy, the change in Gibbs free energy at standard condition denoted by delta G naught. It can be written as NFE naught reduction. Here delta G is indicated at standard condition, it is denoted as delta G naught. We know that the standard electrode potential, it is denoted by E naught. So here this delta G naught equal to minus NFE naught reduction. So this is equation 3. This is equation 3. So where the E naught reduction, E naught red is reduction potential measured at standard conditions. It is also called a standard reduction potential. Standard reduction potential. So in reversible equilibrium reaction, for a reversible equilibrium reaction, want half isotherm says the delta G equal to delta G naught, delta G equal to delta G naught plus RT log K, RT log K. Okay, this is 4. So this is 4. So we are saying that here oxidation and reduction reactions are in equilibrium state, and these are feasible. So that's why here for equilibrium reaction want have isotherms phase delta G equal to delta G naught plus RT log K. Here where K is the equilibrium constant. K is the equilibrium constant. What is the equilibrium constant? Concentration of products by concentration of reactants. Concentration of products by concentration of reactants. So what are products? What are reactants? Here we have taken a reduction of metal ion Mn plus n electron gives rise to n moles of metal. So these are products. This metal is product and these are reactants. These are reactants and these are products. So from this we can write equilibrium constant. Equilibrium constant. So concentration of products means concentration of metal, and the number of moles should be written on the power of metal, and concentration of metal ion. Concentration of metal ion. This is the equilibrium constant. What is equilibrium constant? Concentration of products by concentration of reactants. And R is the gas constant. R is the gas constant, and the value of gas constant is 8.314 joule per Kelvin. 8.314 joule per Kelvin. T is the temperature on the Kelvin scale. T is the temperature on the Kelvin scale. So by substituting 2, 3 equations in 4, we can get this equation. So what is that? Minus NFE reduction minus NFE reduction minus NFE reduction equal to minus NFE naught plus RT log, what is K? Concentration of metal to the power of n, and concentration of metal ion. So here minus NFE reduction equal to minus NFE naught reduction plus 2.303 RT log concentration of metal by concentration of metal ion. So by dividing both sides by dividing minus NF, we can get E reduction equal to E naught reduction minus 2.303 RT by NF log concentration of metal by concentration of metal ion. Concentration of metal by concentration of ion. E reduction equal to E naught reduction minus 2.303 RT by NF RT log concentration of metal by concentration of metal ion. So already we know that the activity of the metal or concentration of the metal is taken as unity. Concentration of metal or activity of metal should be taken as unity, means the value of concentration of metal is 1. So if we substitute this value, we will get E reduction equal to E naught reduction minus 2.303 RT by NF log 1 by. So why? Here concentration of metal ion is 1. So that's why we will get this equation. We will get this equation. For reactions conducted at 298 Kelvin but different concentrations, the Nernst equation is, means here the temperature is 298 Kelvin. Temperature is 298 Kelvin, and we know that R equal to 8.314 joule per Kelvin, and Faraday is 96,500 coulombs. By substituting all these values in the Nernst equation, we will get this equation. So total value is E reduction equal to E naught reduction E reduction equal to E naught reduction minus 0.5 E naught. E reduction equal to E naught reduction minus 0.0591 by N RT log 1 by concentration of Mn plus metal ion. 1 by concentration of metal ion. This is for reduction of metal. This equation is used for the reduction of the metal. So if we take oxidation of the metal, oxidation reactions of the metal, what will be the Nernst equation? So if we take oxidation reaction, means metal is converted into metal ion and electrons. Metal is converted into metal ion and electrons. So for this, K equal to concentration of products by concentration of reactants. Concentration of products by concentration of reactants. If we substitute this K value in the Nernst equation, we will get the E cell reaction for the oxidation reaction. So this is denoted by E oxidation equal to E naught oxidation minus 0.0591 by N RT, 0.0591 log RT log concentration of, so the concentration of metal is unity, so concentration of metal ion. So E oxidation equal to 0.05 E naught minus 0.059 by N log Mn plus 1. So this is for oxidation of metal. So here, for clear understanding, here I am taking one galvanic cell. Galvanic cell is A plus B plus gives rise to Cc and Dd. This is one reaction. So in this, AA, BB are converted to Cc and Dd. So these are, here we are taking AA plus BB gives rise to Cc plus Dd. So these are products, these are reactants. So we know that K equal to concentration of products by concentration of reactants. Here concentration of products are capital C power small c, capital D power of small d, and capital A power A, capital B power small b. So this is the equilibrium constant. By substituting K value in the Nernst equation, we will get Nernst formula E naught minus 2.303 RT by NF log concentration of C, concentration of D by concentration of A to the power of A, concentration of B to the power of B. This is a Nernst equation for this galvanic cell. So this is example 1. In this, zinc is converted into zinc plus 2. This reaction, zinc plus 2, zinc is converted into zinc plus 2 and copper plus 2 is converted into copper. Copper plus 2 is converted into copper, means here oxidation reaction is taking place, here reduction is taking place. So in this equation, these two are products and these two are reactants. So by substituting, by taking K value, concentration of zinc plus 2 into concentration of copper, concentration of zinc and concentration of copper plus 2. We know that the solids, the concentration of metals should be 1. So K equal to zinc, concentration of zinc plus 2 by concentration of copper plus 2. So by substituting this K value in the Nernst equation, we will get this equation. E equal to E naught minus 2.303 RT by 2F log zinc plus 2 by concentration of copper plus 2. Here this is 2 came from zinc is converted into zinc plus 2, copper plus 2 is converted into copper. Means 2 electrons are involved in the reaction. That's why the N equal to number of electrons involved in the reaction. So in this reaction, 2 electrons involved. That's why we are taking 2. So this is the Nernst equation for this example 1. So example 2 is 2 Ag plus copper gives rise to 2 Ag and copper plus 2. So here 2 Ag plus converted into 2 Ag and copper is converted into copper plus 2. Here this is reduction reaction, and this is oxidation reaction. In this, 2 silver and ions accepting 2 electrons and forming 2 silver atoms. And copper converted into copper plus 2 by the loss of 2 electrons. Here number of electrons involved in the reactions are 2 electrons. And from this equation, these are products and these are reactants. So we can write concentration of Ag power of 2 copper plus 2 concentration by concentration of silver ion and concentration of copper. So concentration of copper and concentration of silver equal to 1. So that's why K equal to concentration of copper plus 2 and concentration of silver plus 2. Concentration of copper plus 2 by concentration of Ag plus 2 to the power of 2. By substituting this K value, we will get this one. This equation. So number of electrons are 2 and K value is concentration of Ag. Concentration of copper plus 2 by concentration of Ag plus. So here concentration of products by concentration of reactants. Concentration of reactant. So here next reaction is nickel plus copper plus 2 gives rise to copper and nickel plus 2. In this, nickel is converted into nickel plus 2 means it is undergoing oxidation. So number of electrons are involved in this oxidation reactions are 2 electrons, and copper plus 2 is converted into copper. Here also 2 electrons are involved in the reaction. So first we have to write the equilibrium constant. So for this equilibrium constant, concentration of copper into concentration of nickel plus 2 by concentration of nickel into concentration of copper plus 2. So we know that concentration of copper and concentration of nickel are 1. So K equal to concentration of nickel plus 2 by concentration of copper plus 2. So by substituting this in K value in the Nernst equation, we will get this equation. Number of electrons involved in the reactions are 2 and E equal to E naught minus 2.303 RT by 2A log concentration of nickel plus 2 by concentration of copper plus 2. So next topic is applications of Nernst equation. Applications of Nernst equation. The Nernst equation can be used to calculate the following: single electrode reduction or oxidation potential at any condition. Single electrode reduction or oxidation potential at any conditions. And we can calculate standard electrode potentials comparing the relative ability as a reductive or oxidative agent, and also we can finding the feasibility of combining such single electrodes produce an electric potential, and we can calculate EMF of the electrochemical cell, EMF of an electrochemical cell, and we can also calculate unknown ionic concentrations, and also the pH of the solutions and solubility of sparingly soluble salts can be measured with the help of Nernst equation. pH of the solutions and solubility of sparingly soluble salts can be measured by using Nernst equation. So this is one numerical problem. The standard reduction potential of zinc plus 2 zinc and copper plus 2 by copper are minus 0.76 volts and plus 0.34 volts respectively. What is the EMF of the cell? And they have given concentration of zinc plus 2 and copper plus 2. Concentration of copper plus 2 and zinc plus 2. So they have given standard reduction potentials of zinc and copper. Standard reduction potentials of zinc and copper. E zinc plus 2 zinc equal to minus 0.76 volts. E copper plus 2 copper reduction potential plus 0.34 volts. So by substituting this equation, means here this is having negative value, this is having positive value, means the standard reduction potential of copper is more than standard reduction potential of zinc, means copper is acts as cathode. Copper is acts as cathode and this is acts as anode. So we know the formula E cell equal to E cathode minus E anode. So E cathode minus E anode. E cell equal to E cathode minus E anode. So by substituting these values, plus 0.34 minus 0.76 volts. So we will get 1.1 volt. 1.1 volt. So we know the E naught cell. We know the E naught cell and concentration of the electrolytic solutions. So by substituting these values in the Nernst equation, we will get this equation. E cell equal to E naught cell is 1.1, 0.059 by 2 log. Concentration of zinc plus 2 is 0.05. Concentration of copper plus 2 is 0.005. By substituting these values in this, so we will get value, E cell value is 1.07 volts. 1.07 volts. So next problem is write the overall cell reaction for zinc in zinc plus 2 0.2 molar and Ag plus in Ag in Ag plus that is and calculate the EMF of the cell at 250 degrees centigrade. The standard EMF of the cell is 1.54. They have given standard EMF E naught equal to 1.54 volt. And first we have to write the overall reaction for this problem. So what is this galvanic cell representation? In this first one is anode, second one is cathode. So we know that this is acts as anode, this will act as cathode. So anode means zinc is undergoing oxidation and forms zinc plus 2 ions and 2 electrons. Copper plus 2 accept 2 electrons and forms copper metal. These two are half cell reactions. So by combining these two reactions, we will get overall reaction. So zinc plus copper plus 2 gives rise to zinc plus 2 plus copper. This is the overall reaction of this problem. This is overall reaction of this. Sorry, here in place of copper, first we have to write this is not copper, this is silver. This is not copper, this is silver. 2 Ag plus 2 Ag plus 2 electrons, 2 Ag. This is zinc plus 2 Ag. Ag plus and zinc plus 2 Ag. Zinc plus 2 Ag. Here zinc is converted into zinc plus 2 ion. Silver ions are converted into silver atoms, and the overall reaction is zinc plus 2 Ag gives rise to zinc plus 2 Ag. So they have given standard electrode potential, standard EMF, so that is 1.54, and they have given concentration. So by substituting all these values in the equation, we will get, and number of electrons which are involved in these reactions are 2 electrons. Means zinc is converted, zinc plus 2 means 2 electrons are liberated. At the same time 2 Ag plus is converted into 2 Ag, means it is taking 2 electrons, means number of electrons involved in this reaction is 2 electrons. And by substituting these values in this equation, we will get E cell, that is 1.4809 volts. 1.04809 volts. So this is about numerical problems of E cell. Like this, we can solve the problems by using Nernst equation. And thank you.
Like, share and subscribe. Hit the bell icon for more updates.